Yeah, so this is, right, so this takes on only 0, 1, this one is only 0, 1, and this one is equal to the interaction between the two, so it's also 0, 1. I guess, so another thing I should say is if you had a different scenario where, like in this one, in this question, I just had two time periods, I had like 2004 and 2005. And so which year you're in, like basically each, the pre-period just has 1 year and the post-period just has 1 year. But you could imagine having a larger data set where there'd be like multiple pre-period years and multiple post-period years. So in that case, there's sort of various ways you could do it. But I think the easiest way to think about doing it would be, instead of say 2005 here, you could just have like what we call like a post indicator, and then that would just tell you whether you're in a period that corresponds to sometime after when the treatment was rolled out, right? So if the data set here actually ran from like 2000 to 2010, then you could say, well, I'm going to have a post indicator that indicates whether I'm between 2005 and 2010, and then otherwise that indicator is going to be equal to 0 because I'm between 2000 to 2004.
Can you interpret all the parameters?
Yeah, so I assume your question is you would like me to interpret all the parameters? Or? Okay. Yes, so that's a very important thing to be able to do. So the California parameter there, or the beta 1 on California, basically tells you what the average pollution level in California is relative to Nevada before the special blend is rolled out. So you could sort of think of that as like being the pre-period difference between California and Nevada. Then the 2005 indicator tells you how pollution levels change over time when the special blend hasn't been implemented in that state. So it's actually telling you the change in Nevada. So like what you want to think of is like these parameters are telling you between state and over time differences in essentially like the control condition, like before the special blend is rolled out. So before it's rolled out, this gives you the average pollution, this gives you the difference in pollution levels in California versus Nevada, which might be. Let's see. So if you, well, I mean, I think what you would want to, so that would give you, I mean, I think it would. So if you thought about it, so if all the other variables are 0, basically that means that 2005 is 0, right? So then so that means you're looking in 2004 and you're looking at California, and this is always relative to Nevada. So that's going to give you the 2004, the difference in 2004 pollution levels between California and Nevada. And then if you want to think about setting California equal to 0 here, then this thing is also going to be 0, and you're just going to have beta 2, the coefficient on 2005. So that's giving you the change in pollution levels in Nevada between 2004 and 2005. And then this last, the last coefficient here, beta 3, is what's giving you the change in pollution levels in California relative to the change in pollution levels in Nevada. So that's why it's the difference in differences, because your alpha is just the base, the intercept. So in this case, it's going to be Nevada in 2004. Yeah. So I guess that's another way too that you could look at it, which I think it's probably in the notes somewhere, is that you could go through and sort of set each of these variables equal to 0 or 1. So forget about like this one at the end I added in there. So if Nevada is 0 and 2005 is 0, then you just have y is equal to alpha. So that's going to be like the Nevada 2004 level. Then you turn on California. That's going to be alpha plus beta. So it's like a California 2004 level. And then you can turn on 2005, but not California. And that would give you the Nevada 2005 level. And then you turn both California and Nevada on. You sum up like all of these three coefficients, and it gives you California 2005. So then questions B and C are kind of these are like basically trying to test whether you understand what types of factors can cause bias in the diffs and diffs design and what types won't. So question B says you learn that Nevada has particularly bad air pollution because the traffic is always backed up on the Las Vegas Strip. This is always true every year. Is it going to cause bias in your diffs and diffs estimate? And is it going to be important to get data on the Las Vegas Strip traffic so you can control for this variable? So the answer here is that it's not going to cause bias in your diffs and diffs estimate. And the sort of clue here is that it says it's always that this traffic is always present every year. And so you can think of this as basically being a factor that is different for Nevada than California, but it's not a factor that changes over time. It says it's always there year after year. And so we know that the diffs and diffs design is going to basically control for or net out factors that are different between the two states but don't change over time. So because of that, then you also don't need to actually get data on the traffic patterns because you don't need to control for them since they're not going to cause bias. And then C says old cars generate very large amounts of air pollution, something that's actually true. And you learned that California started a program in 2005 that removed a lot of these cars from the roads. Nevada has not started a similar program. Is this fact going to bias your differences and differences estimates? And then the answer here is that yes, this will potentially cause some sort of bias, right? Because we know that the factors that can cause biases are factors that change differentially for the two states between the treated and or the pre and post period. And this is something that's changing for California, but is not changing for Nevada because it never comes into effect in Nevada or is never implemented in Nevada. And so because of that, it could actually cause bias in your estimator. Okay, so I guess so. The last thing I'll just say like a few things about the calculation questions that showed up in the two midterms. So these ones, I mean, I think these ones tend to be the ones that people have the least trouble with, but there can be a couple of like sort of tricky aspects to them. So in like 2010, the thing that people found the trickiest was that actually we hadn't really talked about expected values. So this in part A when it said what is, so in 2010 it's a question about basically somebody who's considering purchasing a car alarm. So this is something that's going to involve externalities for two reasons. One is that it just generates a lot of noise, so it's kind of a nuisance in the neighborhood. But the other is that it actually deters people from stealing the person, like the car alarm person's car, but then it potentially just induces them to steal somebody else's car. And so there's like a negative externality that's being imposed on other people on the same block who don't have car alarms. And so I think there were sort of a couple things that people found tricky. The first things I said is that they weren't quite sure what to do with expected values. But I think since we talked about that, you guys wouldn't have such a big problem with that. But the sort of essential like parameters that go into this question are that there's some cost to buy the alarm. So it's equal to D plus 0.1 D squared, where D is the loudness of the alarm. So the idea here is like it's going to cost you more to buy a louder alarm. And if you had D set equal to 0 so that the alarm had no loudness at all, then the cost would be 0. So setting D equal to 0 is just equivalent to not buying the alarm at all. And so this guy is thinking about buying this alarm, and then he's going to lose $300 if his car is broken into. So the first part says, so loss is $300 if there's a break-in, and the probability of a break-in is going to be equal to 0.2 minus 0.01d. So if he doesn't buy an alarm, then d is equal to 0, and so there's a 20% chance that his car is going to get broken into. And if he does buy an alarm, then if it's a louder alarm, that's going to decrease his probability. So if he buys an alarm that has loudness d equals 10, then he's going to have a 10% probability of getting broken into. 0.2 minus 0.01 times 10 is equal to 0.1. And so in A, it just asks what is his expected loss. So the expected loss is going to be equal to the actual loss if there's a break-in times the probability of a break-in. So it's just going to be 300, which is the loss if there's a break-in times the probability of break-in, which is 0.2 minus 0.01d. Which, if I have done the math here correctly, should work out, I think, is 60 minus 3d. So that's what its expected loss is going to be. And then the other thing that I think people found a little bit tricky is that, so the next part of the question says, well, then what is the expected benefit of purchasing a car alarm of loudness d? So the benefit of purchasing a car alarm is going to be equal to the loss that's avoided from not getting broken into, right? And so what that benefit is going to be is basically going to be 3d. But the way that you could calculate that is basically expected loss if there's no alarm, so if he doesn't buy one. And that's going to be equal to 0.2 times 300 because d is set equal to 0 in that case. So that would be basically $60. And then his expected loss if he buys an alarm of loudness d, which you just calculated at 60 minus 3d. So you already have that. And then the difference between those, so if you did 60 minus 3d, then you would get 3d. So 3 times d, which is the loudness of the alarm, is the benefit. And that's actually an expected benefit because there's only some chance he's going to have a loss.
Why does the net benefit not include the 100% chance that you have to pay for the car alarm? So we're not including it.
Yeah, so no, that's definitely true, but you just said right there, it's the net benefit. So this is just like the expected benefit, it's like a gross benefit of the alarm, but there's going to be some cost to buying the alarm, and so when you calculate the net benefit, then you have to include that. So I think that's in part C, basically. It says Bill maximizes expected net benefits, which are going to be equal to expected benefits minus costs in deciding how loud an alarm he should buy. So what you have is there benefit minus cost, which is going to be equal to 3d minus what we wrote the cost as over here, which I guess is d plus 0.1d squared. So that's what the net benefit or the expected net benefit is going to be. And then to solve what he's going to, or what loudness alarm he's going to buy, you just take this thing and you differentiate it with respect to d, set the derivative equal to 0. So you're taking the whole thing, the net benefit's benefit minus cost, differentiating that with respect to d, set that equal to 0, and I think what you should get is d equals 10 when you do that. And then in part D, it starts like introducing these potential externalities. So the first externality that gets introduced is the noise nuisance. So let's suppose that his car alarm is going to generate noise that imposes a cost of n equals 0.1d squared on his neighbor. What tax should the government charge Bill to fully internalize the noise cost? And facing this tax, will he choose to purchase the car alarm? And if so, how loud will it be? So the tax that should be charged should always be equal to the damage that's being done. And so in this case, it's told you that the noise is doing basically like creating a nuisance that's worth 0.1 times d squared to Bill's neighbor. And so what that tells you is that the tax should then be set at 0.1 d squared. And yeah, so I mean, so sometimes it's like, so the tax should be equal to like the marginal damage that's being done. And so maybe like it might seem a little bit confusing. I said, well, the tax is going to be equal to total damage that's being done here, but that's the reason that it's that way is that in the initial state there is no noise nuisance at all. So the marginal damage is basically going from like an initial state of no car alarm noise to whatever the car alarm noise will be conditional on, like what loudness alarm he buys. Because you took the derivative before, right? So the marginal tax would be equal to that, like the tax per, like the total tax you would pay. So I mean, so it's important to sort of keep in mind like what the total benefits are and what the total tax is versus like what the marginal benefits are and what the marginal tax is. So like what you gave is correct for the marginal tax, and it would correspond, and so that would be like if we calculate the marginal cost and then figure out the marginal tax, so like the tax per extra decibel is going to be equal to 0.2d. But the way that it's set up, it's asking you like what is the value of the like a total externality, and then you're going to introduce that into his total net benefits thing after you impose the tax. Did you have questions? Right, so the per decibel tax, or the tax for each additional decibel. Okay, so let me just write, so the tax here, the total tax is going to be set at 0.1 times d squared, and then his new like net benefit function is going to take into account not just the benefit minus the private cost of the alarm, but then he also now has to add in this additional tax that he's going to pay that varies with loudness d. So that's going to be the new net benefit function, so it'll be like 3d minus d minus 0.2 d squared. And then, so the marginal tax, let's say, is going to be equal to 0.2d. So once you take the derivative of this thing, it's going to be like the marginal benefit will be 3 because of 3d there, and then the marginal private cost will be 1 plus 0.2d, and then the marginal tax, which is this last part is the tax, that'll be 0.2d. So the marginal tax there is 0.2d, and what that's showing you is that the tax that he pays is actually increasing. Well, the tax is always increasing in the amount of the noise, but as it gets noisier, the marginal tax per decibel that he pays actually starts increasing because the damage function is basically convex. Okay, so I have office hours now too from 4:10 to 5 if you guys have additional questions.